To ensure that products meet specifications, process materials are routinely sampled at various stages of the production process. The samples are then tested to determine whether corrective action is necessary. pH is a term used to describe the relative concentrations of hydrogen ions and hydroxyl ions present in a liquid. A hydrogen ion is a positively charged hydrogen particle. A hydroxyl ion is a negatively charged particle made up of oxygen and hydrogen atoms. The relative concentrations of hydrogen ions and hydroxyl ions determine whether a liquid is acidic or alkaline. A pH scale is used to indicate the acidity or alkalinity of a liquid. The numbers on the scale range from 0 to 14. A pH less than 7 indicates that a liquid is acidic. An acid has a greater concentration of hydrogen ions than hydroxyl ions. A pH greater than 7 indicates that a liquid is alkaline. An alkali has a greater concentration of hydroxyl ions than hydrogen ions. A pH of 7 indicates that a liquid is neutral. This means that the concentrations of hydrogen ions and hydroxyl ions are essentially equal. pH tests are made for various reasons. For example, some processes require a specific pH to be maintained so that certain chemical reactions can take place. And in some systems, the pH of processed liquids must be maintained at a certain value to prevent corrosion of system components. A pH test is typically made with a pH meter. This pH meter consists of a digital display, controls, a probe that is inserted into a sample to measure its pH, and a temperature probe. Temperature can affect the accuracy of a pH measurement, so this meter's internal circuitry automatically compensates for any variations in temperature. Before a pH test is conducted, the probes must be cleaned to make sure they're free from materials that could contaminate the sample and cause an inaccurate reading. Generally, distilled water is used to rinse any foreign materials from the probes. Then the probes are patted dry with a lint-free tissue. Once the probes are clean, the next step is to standardize the pH meter. A pH meter is standardized using a solution called a buffer solution, which has a known pH. Generally, a buffer that is close to the expected pH of the sample should be used. In this example, a buffer that has a known pH of 4 is added to the beaker. The beaker is placed on a magnetic stirrer to make sure the solution is homogeneous. This, in turn, helps to ensure an accurate pH measurement. After using the meter controls to enter an expected pH value of 4, the probes are immersed in the buffer. The pH meter is then standardized for the temperature and pH of the buffer solution. All that's left to do before the sample is tested is to clean and dry the probes again. Now the sample can be tested. The probes are inserted into the sample. The meter is then used to determine the pH value of the sample solution. A reading of 4.2 indicates an acidic liquid. The results of the pH test are compared to specifications to see if the process is within acceptable limits. A percent solids test determines the amount of solids in a solution. These tests are often done for process systems involving chemical reactions that produce precipitates. A precipitate is a solid substance that falls out of solution during a chemical reaction. A percent solids test can indicate how well the chemical reaction is taking place by measuring the amount of solids that have fallen out of solution. The test involves several steps. Generally, this type of test is performed by passing the sample through filter paper, which traps the solids. The solids can then be weighed. To prepare for the test, a fresh piece of filter paper is dried in an oven. This removes any moisture from the filter paper, so that the actual weight of the paper can be determined. Plant procedures usually specify how long the filter paper must be dried. Another preparatory step is weighing a clean beaker. This particular beaker weighs 0.222 kilograms or 222 grams. This weight is written down. Next, the sample is poured into the beaker and the beaker is weighed again. Together, the beaker and the sample weigh 0.608 kilograms or 608 grams. The purpose of these two steps is to determine the actual weight of the sample. You can determine the weight of the sample by subtracting the weight of the empty beaker from the weight of the beaker with the sample in it. The calculated weight of this sample is 386 grams. After the filter paper is dried for the specified amount of time, it is weighed. This particular filter paper weighs 0.9572 grams. Next, the filter paper is placed in a funnel. Then a rubber tube connected to an aspirator is attached to the funnel assembly. The aspirator is used to help draw the sample liquid through the filter paper. Now the technician is ready to filter the solids out of the sample. First, the sample is poured into the funnel. The liquid passes through the filter paper, and the solids remain trapped on the paper's surface. After the sample is drained, the beaker is rinsed, and the rinsed liquid is poured into the funnel to remove any remaining solids from the beaker. In this example, distilled water is used to rinse the beaker. However, some samples may have to be rinsed with a different liquid. Next, the funnel assembly is rinsed to wash the solids from the wall of the funnel and ensure that all of the solids have collected on the filter paper. The filter paper containing the solids is removed from the funnel and returned to the oven to dry. This removes moisture from the solids and the filter paper so that the actual weight of the solids can be determined. Again, plant procedures generally specify how long the filter paper and solids should be dried. After the filter paper and solids have dried for the proper amount of time, they're weighed. In this case, they weigh 1.5738 grams. Now, the actual weight of the solids can be determined by subtracting the weight of the filter paper from the weight of the filter paper and the solids. In this example, the solids weigh 0.6166 grams. Next, the actual weight of the solids is divided by the actual weight of the entire sample. Then the answer is multiplied by 100 to determine the percentage. In this example, the sample contained 0.160% solids. The results of the percent solids test are used to see if the process is within specifications. A pH meter is standardized using a solution called a buffer solution, which has a known pH. Generally, a buffer that is close to the expected pH of the sample should be used. Now, the actual weight of the solids can be determined by subtracting the weight of the filter paper from the weight of the filter paper and the solids. In this example, the solids weigh 0.6166 grams. Next, the actual weight of the solids is divided by the actual weight of the entire sample. Then the answer is multiplied by 100 to determine the percentage. In this example, the sample contained 0.160% solids. Specific gravity tests are helpful for process systems in which the final product is a liquid. This is because the specific gravity of a liquid can indicate the relative amounts of materials in the liquid or the purity of the liquid. Specific gravity is the ratio of the density of a substance to the density of water at a standard temperature. For example, at a standard temperature, the density of this alcohol is 0.79 grams per cubic centimeter, and the density of water is 1 gram per cubic centimeter. To find the specific gravity of the alcohol, we use the ratio of the density of the alcohol to the density of water. When the division is done, we get a specific gravity of 0.79. A specific gravity of 0.79 means that the alcohol is 0.79 times as dense as the water. Now, the density and the specific gravity of a solution can vary according to the relative amounts of substances in the solution. For example, when alcohol and water are mixed, the specific gravity of the solution that is formed is directly related to the amounts of alcohol and water in it. Since alcohol is less dense than water, the specific gravity of the solution decreases as the amount of alcohol in the solution is increased. One instrument that's often used to perform specific gravity tests is a hydrometer. A hydrometer basically consists of a float and a stem, which has a specific gravity scale. To run a specific gravity test, the sample is first poured into a container. Then the hydrometer is lowered into the container. The density of the sample determines how high the hydrometer will float. A hydrometer will float higher in denser liquids. The specific gravity indication on the hydrometer scale for this sample is 1.056. The temperature of the sample must be compensated for. The specific gravity of a liquid is related to its density, and the density of a liquid changes as its temperature changes. In this case, the temperature is 22 degrees Celsius. Compensating for temperature means adding a correction factor to or subtracting a correction factor from the indicated specific gravity. Let's look at an example. Correction factors are usually provided in charts. To use the chart, locate the temperature of the sample and then the corresponding correction factor. In this example, the temperature is 22 degrees Celsius. So the correction factor is minus 0.002. Subtracting 0.002 from the indicated specific gravity of our sample, 1.056, gives us the actual specific gravity of the sample, 1.054. From here, the result of the test is compared to the specifications to determine if the sample is within acceptable limits. A titration is a test that uses a chemical reaction to determine the concentration of a solution. For the purposes of this program, we'll define concentration as the amount of one material dissolved in another material in a solution. One way titrations are used is to determine the concentration of an acid or an alkali through a neutralization reaction. Let's look at a typical titration used to determine the concentration of an alkali. We'll analyze a sample that has a volume of 100 cubic centimeters or 100 cc's. To perform the titration, we'll use a burette, which is a graduated glass tube with the valve at one end. We'll also use a mixer, an indicating solution, and a supply of acid that has a known concentration, in this case, a concentration of 0.01825 grams per cubic centimeter. The burette is filled with the acid. Then the beaker containing the sample is placed on the mixer and the mixer is started. Next, the indicating solution or indicator is added to the sample. For this test, 3 drops of phenolphthalein are used. Methyl orange and methyl red are other examples of indicators. The purpose of an indicator is to change the color of a liquid to give a visual sign that a chemical reaction is complete. When the reaction is complete, the color produced by the indicator completely disappears. Since our example involves a neutralization reaction, the reaction is complete, or the endpoint is reached, when the alkali in the sample has been neutralized. After the level of acid in the burette is checked, the titration can begin. The valve on the burette is opened, allowing the acid to drain into the beaker. When the color of the sample begins to change, the valve is closed almost completely. The valve is left open just slightly to allow the acid to drain out a drop at a time. When all traces of the color produced by the indicator have disappeared, the reaction is complete. The alkali in the sample has been neutralized. As soon as the color of the sample changes completely, the valve is closed all the way. Now the amount of acid required to neutralize the alkali can be determined. By checking the level in the burette, you can determine how much acid was used. In this example, 26 cc's of acid were used. To determine the concentration of alkali in the sample, we can use this formula, which states that the concentration of the alkali times the volume of the alkali sample equals the concentration of the acid times the volume of the acid used to neutralize the sample. We can substitute the known values from our example and then calculate the concentration of the alkali, which in this case is 0.004745 grams per cubic centimeter. In the example we just saw, the titration was performed manually. In some situations, titrations are performed using automatic devices. This is one example of an auto-feed titration device. Its purpose is to feed an acid or an alkali of known concentration into the sample to be tested. This device measures the conductivity of the sample to detect the endpoint of the neutralization reaction. Specific gravity is the ratio of the density of a substance to the density of water at a standard temperature. An indicating solution or indicator is added to a sample to give a visual sign of when a chemical reaction is complete. The reaction is complete when the color produced by the indicator has completely disappeared. Sometimes it's necessary to determine the concentrations of several materials in a complex solution or mixture. A gas chromatograph is often used to perform this type of test. Let's take a look at a simplified illustration of a gas chromatograph to see how it works. In this illustration, there's a carrier gas supply, a sample inlet or injection port, a sample heater, a tube called a column that's filled with material called packing, a thermal conductivity cell, and a recorder. During operation, the carrier gas carries the sample to be analyzed through the column and the thermal conductivity cell. The carrier gas is a gas that won't react with the sample material. Helium and nitrogen are commonly used as carrier gases. The sample inlet, or injection port as it's commonly called, is where the sample is injected into the gas chromatograph. The gas chromatograph requires a sample to be in the form of a gas, so the heater is used to vaporize liquid samples. If a liquid sample cannot be vaporized, the test can't be run. The vaporized sample is fed into the flow of carrier gas, which carries it on through the system. The packing material in the column separates the different materials in the sample gas mixture as the mixture flows through it. Activated carbon and silica gel are commonly used as packing materials in gas chromatographs. Different materials flow through the packing material at different rates. This causes the parts of the mixture to separate from each other. The thermal conductivity cell is where each material is detected as it comes out of the column. As each material enters the cell, it cools a sensing element in the cell. The sensing element's temperature change, in turn, alters the amount of resistance to current flow through the sensing element. The amount of change in resistance indicates the amount of material coming out of the column. The recorder compares the amount of each material with the size of the sample and displays the concentration of each material. This is a gas chromatograph. Let's take a look at its components. Then we'll see how it's used to perform a test. A tank of helium is the carrier gas supply. The helium is fed in at the back of the gas chromatograph. This is the injection port, where the sample is injected into the gas chromatograph. The column filled with packing material and the thermal conductivity cell are located inside, but this is what a typical column filled with silica gel looks like. And this is the recorder. The test results are printed out on this paper. The recorder has a control panel with keys that are used to set up the gas chromatograph for specific tests. Before the gas chromatograph is used to test a sample, it must be calibrated or standardized. The procedures used to standardize a gas chromatograph are specific to the instrument being used, so be sure to check the manufacturer's instructions for your gas chromatograph. Once the gas chromatograph has been standardized, it can be used to accurately measure the concentrations of the components in the sample. A syringe is used to draw off a small amount of the sample, which is then discarded to waste. This procedure is performed several times to ensure that the syringe is free of any foreign materials that could contaminate the sample. Next, the syringe is filled, and then some of the sample is forced out of it to remove any air trapped in the syringe. The sample is then injected into the sample port. As the sample passes through the instrument, the recorder prints out the test results. This is the printout for the sample that was just run. It includes a plot of the actual test. Each horizontal marking on the paper represents the concentration of one of the materials contained in the sample. The bottom of the form also contains data that indicates the concentration of each material in the sample. As you can see, the majority of the sample, over 98%, is one material. This material is the finished product from one of the process systems in this plant. The rest of the materials, all less than 1% each, are byproducts or impurities. The values on the printout can be compared to process specifications to determine if they're within acceptable limits. Let's take a look at a simplified illustration of a gas chromatograph to see how it works. In this illustration, there's a carrier gas supply, a sample inlet or injection port, a sample heater, a tube called a column that's filled with material called packing, a thermal conductivity cell, and a recorder. This is the printout for the sample that was just run. It includes a plot of the actual test. Each horizontal marking on the paper represents the concentration of one of the materials contained in the sample. The bottom of the form also contains data that indicates the concentration of each material in the sample. When phenolphthalein is used as a visual indicator in a titration, how can you tell when the chemical reaction is complete?